right, good afternoon, everyone. Hope you're having a great conference. So today I'm going to be talking about some design and architectural considerations for running highly available stateful applications in Kubernetes. Over the last few years, we've made tremendous strides supporting stateful workloads, and adoption has been increasing every year. Portability and self-healing are one of the most compelling aspects of Kubernetes. And as you learned from the keynote earlier this morning and the Storage 101 session earlier today, in storage, persistent volume claims provide that portability layer for Kubernetes storage. However, that doesn't mean you can completely forget about storage. You still need to understand what storage options are available to you, what are their various trade-offs, and what is best for your application. So today, I'm going to try to answer some of those questions. I'll first give an overview of the various options that we support today in Kubernetes, and then I'm going to deep dive into building highly available stateful applications, specifically focusing on how to achieve failure domain spreading with storage. I'm going to give a demo of various real storage systems that are in Kubernetes today and demo how they behave in different failure scenarios. And then I'm going to end with a discussion on pod downtime and how to build recovery into your application. So let's dive right into what we support in Kubernetes today. There are a lot of options available to you. We have over 15 in-tree storage drivers and over 35 CSI drivers, and the count keeps on increasing. These drivers interface with a wide architecture of different storage systems, ranging from local to remote storage, cloud services to network appliances, software-defined storage systems, distributed systems, hyperconverged systems, the list goes on. So with all of these various options available to you, how do you go about picking what is the best for your applications in your environment? Let's break down these systems into various characteristics that can help narrow down your choices. So here are some characteristics that I think are especially important for building a highly available application. First is accessibility. This is about how close your application needs to be to the underlying storage backend. Does it need to be in the same node? Does it need to be in the same rack or zone? Or can it be anywhere in the cluster? This is very important because this will determine how flexible your application pods can be placed in the cluster, especially when there's a lot of moving parts and you might have different node failures going on. Next is availability. This is about how resilient your storage system is to different cluster failures. Can your storage system survive a node failure or a rack failure or a zone failure? Oftentimes, availability is very close and very similar to accessibility, but that's not always the case, and I'll provide an example of this later. Then we have durability. This is about the data replication factor underneath and how many disks can fail before you've completely lost your data. And then we have access mode. Access mode determines how many nodes can simultaneously mount the volume at the same time. And this is important because it's going to restrict how many replicas of your application you can have running concurrently. All right. And some other important characteristics that you should always be considering also with any system is performance and cost. So now I'm going to go into some examples of specific storage systems and where they fall into these various characteristics. Let's start with local disks. A local disk is directly attached to a node, And it generally offers the best performance and the best cost. However, it has the worst availability and durability. If that disk or that node fails, then any pod using that disk is also unavailable. It's important to also point out that in many cloud environments, the local disk offerings are not durable beyond the life of the VM, which means that if that VM gets terminated or the physical host has an error, then all the data on that local disk is completely lost. So this is something you really need to carefully consider if you want to use local disks in your application. Next, we have cloud disks. These are generally block devices that show up as block devices in your VM, but underneath are actually remotely accessed over the network. Typically, they are restricted to a single zone, but they are replicated within that zone. So compared to local disks, cloud disks have improved durability and accessibility, but the performance may not be as good and the cost is a little more. Some examples of cloud disks include GCEPD, AWS EBS volumes, and Azure disks. Some cloud providers also have a replicated cloud disk offering, such as GCE regional PDs. These types of disks actually synchronously replicate the data across multiple zones. So you have improved accessibility and availability, but the performance may not be as good because now you have to have synchronous replication whenever you write, and the cost is also increased because now the disk is taking up twice as many. Next, we have a single NFS server. Access is greatly improved because you can mount that NFS share from anywhere in the cluster. You can also have multiple mounts of the same share across multiple nodes at the same time. However, this single server remains a single point of failure in your system. So this is one example where availability and accessibility are not the same. Cost compared to a cloud disk, or let's say durability, also depends on what the underlying block device is that's backing your NFS server. If, say, we use a cloud disk to back it, then we'll have that 3x durability within that zone. And cost is a little more expensive because now we have to pay for compute and network resources. And in terms of performance, now you have an extra overhead of some network protocol on top, and you might also have traffic coming across various zones. Lastly, we have scale-out or HA filer systems. When you configure it as such, you can have global accessibility, global availability, and durability. The performance varies a lot depending on what the actual underlying system is, but there are a lot of options available in this space, both commercial options and open source options. But generally, the cost of these systems are the most expensive because they're generally the most complex software-wise. So now that you have an understanding of some of the storage options that are available in Kubernetes, now you can use that information to decide what is best for your application. But before we get into that, first, when you're building a highly available application, it's very important to consider to build redundancy into the system and to avoid single points of failure. So in Kubernetes, one way that helps achieve that goal is pod anti-affinity. This gives you the ability to spread your application's pods across different failure domains so that a failure in one area does not take down your entire application. In this particular example, the failure domain is zone, as specified by the topology key. But it can also be node, it can also be rack, it can be any topology you define in your environment. This feature just leverages the same Kubernetes labels that you use for anything else. So let's go into some common stateful application architectures, see how they can use pod affinity, and see how that works with some of the various storage options that we discussed. So the first type of application to consider is one that follows the 12-factor model. This is where the application does not store any unique state between all its replicas. So all of the replicas can share the same storage backend. And some examples of these are content management systems. These applications do not provide data redundancy at the application level. So they depend on the storage layer to provide that high availability and data redundancy features. Storage systems that are really good for this type of application are multi-writer systems that are globally accessible and available. So the scale-out or HA filer systems will fit well into this model. And to deploy this model in Kubernetes, the best way to do that is to use a Kubernetes deployment. In a Kubernetes deployment, all of the pod replicas are the same, including what volumes they use. So you can see here in this example, all the pods are spread across different zones, but they're all sharing the same persistent volume claim. And what that means is that this persistent volume claim also has to be accessible across all of those zones. And when one of the zones becomes unavailable, then this application is still able to continue serving its data because the storage layer is providing that high availability, and these other replica pods in these other zones are still able to access their storage. So it's important to point out here that deployments are good with multi-writer volume types. Single writer volume types do not work well with this model because they can only be accessed from one node at a time, which means that you would be restricted to only having one replica in your deployment, which will not give you high availability. Instead, single writer volumes are better suited for distributed applications. These are applications that shard and replicate their data between the application pods. Some examples of these include distributed databases like Cassandra and Mongo, just to name a few. And these applications do not need high availability at the storage layer because they've already built it in to the application layer. So the single writer volumes are great for these. They don't have to be globally accessible or available. So you can choose potentially cheaper and more performant options such as local disks or cloud disks for these types of applications. And in Kubernetes, the way that the stateful sets are the way that best support distributed applications. The main difference between stateful sets and deployments are that two main things. One, every pod in a stateful set has a unique and stable identity. And then second, every replica in a stateful set has its own unique persistent volume claim. So you can see in this example that we have pod 0 using PVC0, pod 1 using PVC1, and pod 2 using PVC2. If any of those replicas dies, it's going to come back with the same name, and it's going to come back with the same storage. And in this case, if one of the zones goes out, the application is still able to serve the data from its remaining shards, and you can bring up new pods to replace the failed one, and potentially new disks to replace the failed one. And those new replicas will end up reconstructing the data and rejoining the application cluster. So this wasn't always easy to do in Kubernetes, especially when using volume types that were not globally available or accessible in the cluster. Kubernetes originally assumed that you can access volumes from any node. But now with the volume topology feature, we've added intelligence into the scheduler so that it can better understand these more constrained volume types. There's no user configuration that you need to use this feature. It's the underlying storage provider is giving this information to Kubernetes. But now you will be able to auto-scale your replicas and dynamically provision those volumes across zones. All right, so now I'm going to go into a demo. I'm going to demo applications that are not highly available. And the reason for that is I want to be able to show you how some real storage systems behave in certain scenarios, so that you can see that behavior without the application layer doing the redundancy. And you can decide if that's a model that is best suited for your application. So in my initial setup in my cluster, I have 6 nodes spread across 3 zones. And I have 4 stateful sets, each with 1 replica. And each of the 4 stateful sets are using a different type of storage class. I have 1 storage class that uses local disks, 1 that uses a single zone volume, another one that uses a multi-zone volume, and the last one, which is using an NFS volume that's globally available. So let's go into the cluster. All right. Okay, so let's take a look at my nodes again. So you can see I've got 6 nodes spread across 3 zones, 2 nodes each. Let's take a look at my pods. So I've got 4 pods, and you can see I've labeled them. I've named the pods with the name of the type of storage that it's using. And if we take a look at the actual disks themselves, I've also got 4 PVCs. Let's take a look at the PVs for fun. So let's look at the local disk first. You'll see here that this volume has a type of a local volume. It has a path to that disk on that node. And it has this node affinity field filled into it. And you can see this node affinity is basically telling Kubernetes that any pod using this volume can only be scheduled to nodes that have the label hostname with this value. So this is information that the storage provider inserted itself. This is not something that you as users have to specify in your PVCs. But basically, you can see here this local volume is restricted to this single node. And if we take a look at the next volume, let's look at our single zone volume. You can see here that this type is a cloud disk. It's a GCE persistent disk. And it also has node affinity. But instead of having node affinity on a single node, it has node affinity in a single zone. And here it's saying the zone is Europe West 1C. So this tells the scheduler that pods using this type of this volume can only be scheduled within that one zone. And if we look at our next one, which is our multi-zone disk, you will see that this is also a GCE persistent disk. It's a special flavor of it called a regional PD. And the special thing about it is that it can be accessed from 2 zones. So if you have a node, if you have a complete failure in one of the zones, you can have replacement pods come up in a second zone. And lastly, we will look at the NFS volume. Here we can see it's an NFS volume. Here's its IP. And there is no node affinity on it. This is telling the scheduler, you can schedule pods using this volume anywhere. All right, so that is all the volumes on my system. Now I'm going to have some fun and fail some nodes. So let's look. All right, okay, I got my 4 pods. You will notice that I've initially scheduled all 4 pods on the same node. You probably don't want to do this in production, but I'm just doing it to demonstrate. So I'm going to go ahead and fail this node. Does anyone want to take a guess what's going to happen? Anyone? Anyone? Yeah.
The local one should not be able to come up again, while the others should be able to come up on another node.
Yes, that's right. The pod using the local volume is not going to be able to come up after I've failed this node because the disk that it needs is on that node, which is now unavailable. But the other pods, since they are accessible to more than one node, are going to be able to recover. So let's go ahead and fail that node. All right, so you can see that all the pods have immediately are terminating and restarting. So while we're waiting for that, I just wanted to point out the way I failed this node is by using a node taint. This is a mechanism in Kubernetes to apply special conditions to nodes. So you can see here, we have this kubectl taint command, and you specify what node you want to taint, and you give it a condition. And I just made up some condition. And the other thing you can, the other thing that's associated with a taint is an effect. And I think the 2 main effects that are supported today are no schedule, which means it tells the scheduler if a node is tainted, don't schedule any more pods to this node. And what I've used here is the no execute effect, which means not only don't schedule any nodes to this, or don't schedule any pods to this node anymore, but also evict all of the pods that are on it because this node is unhealthy and I don't want anything running there anymore. Let's see what's going on. Okay. My pods are still pending. Let's take a look at one of the pods and see what's going on. Oh, that's fun. Okay. So I accidentally tainted all of the nodes in my cluster. Let me go reset this. All right. Let's try this again. I'm going to go and taint or fail one node. Okay. All right, here we go. So we see this NFS pod has so far been able to recover. We'll wait for the others. Well, I guess while we're waiting for the others, let's look at the, so we said that we expected the local pod to not be able to come up. Let's take a look at that. Oops, I can't spell. So we'll see that the local pod has failed scheduling because one of the nodes has a taint on it, and the other remaining 5 nodes in my cluster cannot access that volume. All right, so I think the remaining 3 pods were able to recover. Now let's clean this up a little bit. Okay. So we have 3 running pods now. The local pod is gone. Now I'm going to go and taint the next node. This node that I'm going to taint is going to be the second node in that zone, which is going to take out all of the nodes for that zone. So let's fill another node. Okay, now all the pods are restarting again. And what should happen this time now is that the single zone pod is going to fail to come up because now the whole zone is gone. But the other 2, my multi-zone pod and my NFS pod, should still be able to recover. Let's take a look at it. Okay. So what happened there was that when the first time I failed the node, it got rescheduled to a completely other zone. So when I failed the whole zone, these 2 pods they did not have to restart because they were not in the zone that I failed. So yeah, now we can see, let's take a look at my single zone pod. And we can see it failed scheduling because 2 of the nodes that it could run on have taints on them, and the remainder of the remaining 4 nodes cannot access that single zone pod. All right, so as you can see from that demo, it's really important to consider when you're choosing a storage system to consider their availability and accessibility characteristics, and see if your application can handle that. So let's go back to the presentation. That's not it. Okay. All right. So while we're on the topic of pod failures, now I'm going to talk about pod downtime and why it's important to factor this into any application's architecture. The total time that a pod is down consists of the time to detect failure and the time it takes to replace that pod. And from the demo, the time to detect failure was essentially 0 because I manually tainted the node when I wanted to fail it. But in a real production environment, there has to be something that is monitoring those nodes, and that something also has to, after some threshold period, go ahead and taint that node as unhealthy in order to trigger all the evictions of those pods. So that's going to add some time to your downtime. And then to bring up a new pod, you kind of saw a little bit of this in the demo. Some pods were faster to come up than others. The single writer volume pods have to first, because they're only accessible on a single node, in order to bring it up on a new node, you need to detach it from the first node and then go and reattach it to that second node. So you might have noticed that the NFS pod was able to come up a lot faster because it doesn't have to go, it can mount multiple, on multiple nodes at the same time, and it doesn't have to wait for this detach and reattach. So all of this factors in to the total downtime of your pod. So it's very important to build this in when you are figuring out what your what your maximum degraded downtime state can be. And there's one more caveat that I want to point out, especially with stateful sets. So many stateful applications require exactly once semantics. What this means is that it cannot have two containers write to the same volume. Otherwise, it can cause data corruption to that disk. So the way that this is supported in Kubernetes is that when you delete your pod, that pod object doesn't actually get deleted immediately. What happens is that it gets into a termination phase or terminating phase, and then kubelet on that node will start tearing down the containers, and then once those containers are torn down, it's going to tear down the volumes. And kubelet is going to be the one that finally deletes that pod object from the API server. Only after it has confirmed all the containers are not running anymore and all of the volumes are unmounted. However, if kubelet itself is unresponsive, then you have this split brain scenario where you don't know if the node is still healthy, but it's just partitioned and the applications are still running fine, or the node is actually down and you want to recover your application. So when kubelet is not responsive, it's not able to delete that pod object, and then the stateful set controller is not able to create a replacement pod for that until kubelet is able to acknowledge that the pod is actually not running anymore. So a common way to solve this is a technique called node fencing. This technique ensures that the workload containers are not running on that node anymore. In bare metal environments, this is often achieved by using an IPMI power reset to the server. And in cloud environments, something similar can be done by deleting the VM. But because this is environment specific, there is no common solution in Kubernetes. Many Kubernetes providers have built functionality on top to give this capability. As an example, GKE has a node auto repair feature that will go and kill your VM after it has detected the node to be unhealthy for 10 minutes. So, adding all of these factors together, recovering a single stateful set pod can take on the order of minutes or even hours if you don't have such an automated solution and you need to go in and manually recover them. So for that reason, it's very important that when you're designing your highly available application, you don't depend on the availability of a single pod, because that single pod will become your single point of failure. All right. So in summary, while the stateful workload experience is not completely seamless, we've made many improvements in Kubernetes over the last few releases to make this better. We have features like volume topology, pod anti-affinity, and node taints that will help with in making it easier to deploy and manage your highly available applications. We also covered some high-level architectural models of deploying stateful applications using pod anti-affinity. And we discussed when it's appropriate to use a deployment versus a stateful set, and also consider when you're designing applications to have the data redundancy either at the storage layer or at the application layer. And perhaps most importantly, when you are designing an application, a highly available application, be sure to build redundancy into your system and account for downtime of your individual replicas. So doing so will make your applications more resilient in the long run. So that's it. For more details on the various specific topics that I covered today, feel free to, these slides are available on the schedule, so you can go ahead and click on any of these links for more information. I covered a lot of topics across a lot of SIGs. So I think everything I covered here generally falls under the realm of SIG storage, SIG apps, SIG node, and SIG scheduling. If you're interested in any of these specific topics, you can join the community meetings and the Slack channels to ask for anything. And if you want to get involved in the project, you can also feel free to reach out to me, and I can help point you in the right direction. Right, so I'm going to leave the remainder of time for questions.
Hi, thanks for the talk. There are some cases like when running in AWS where some of these storage drivers like the Elastic File System for AWS is in alpha since a month, so this storage class is not available. So you have to be playing with selectors and a particular pool for this. There's some other way to play with MFS in this case when there's storage class are not available for your provider.
Oh, sorry, I'm not able to catch. I think it's.
There are, for example, if we have the clusters in AWS and some of these drivers, like the Elastic File System, the MFS, are not available or in alpha versions, which really are earlier stage. So we ended having a separated pool with an MFS mounted, and the pod basically mounts a host path, and is the way you can use a network file system with AWS.
Oh, I see. So you're asking specifically because the EFS CSI driver is still alpha?
Yeah. Then
what is the best way to use that?
Exactly.
I'm not very familiar with AWS, but I would say so my understanding is that EFS is like an NFS type of thing.
Yeah, exactly this.
So I think that there's an in-tree NFS driver that you can use to just generally mount NFS shares. It works across it doesn't actually care what that backing NFS server is. It just needs an IP and a share. I'm not sure if EFS has any special protocols or permissions that you need the special driver for, but.
I will need to take a look too.
Okay.
Anyway, thank you.
But I can, if you want to sync up, I know the person who's working on the EFS driver. I can, yeah.
Yeah, and related to that question, if you need to expose some storage, read-write too many pods, for example, in the case where you were talking about the CMS, would it be logical to have some multi-zone disk, have a pod running on an FS server, and maybe the cluster making a persistent volume claim for it?
Let's see. So you're asking about how to make an NFS server more available across multiple zones.
Yeah, and inside the cluster. I mean, running the NFS server not outside the cluster, but inside the cluster in a pod.
Yeah, so there are various open source scale-out NFS solutions. I think Ceph and Gluster are some popular ones, where they basically take inventory of all the local disks and then present this, scalable NFS layer on top of it. So that's one way to do it. The other common way I see people do this in Kubernetes is to deploy a single NFS server using some cloud disk that's backing it. So like I mentioned, like that single NFS server is a single point of failure. If you use something that is a single zone cloud disk, then if that zone goes down, then your NFS is down. If you use like a replicated cloud disk solution like regional PD, then you are more resilient to that single zone failure. So now you can, if that whole zone fails, your NFS server pod can get scheduled to a different zone, and that regional PD can access that. There's still downtime though. There's still some downtime because the regional PD is still a single writer volume, so you have to detach it and reattach it. So it's not going to be like completely a seamless failover.
Okay. Just one last question here. On your right. Far, far away.
So I'm wondering about this potential split brain situation. Then if you're not worrying about something writing to a volume, but you are worried about something updating a database through over a TCP connection to some other pod that's still alive, does Cordon help? Can you use that?
So I think if you don't actually care about the volume layer, but you care about the application layer writing to a database, then that's something where you might still need to build in some concurrency in your application. So like having some sort of leader election or distributed locking system.
All right. Thank you very much. If you have any further questions, you can catch her outside.